All right, thanks for coming, guys. We're going to get started. A little behind schedule. My name is Toponce, and I'm going to be talking about how to correctly hash stored passwords. Title of my talk is Security Through Obesity. We've probably heard the term security through obscurity, where in and of itself, that's actually not security, right? In this case, I'm going to talk about security through obesity, where we want bloated algorithms to provide us with security, and it'll probably make sense as we go along. My presentation, for those of you who might have attended my talk yesterday, this presentation is licensed also under the Creative Commons Attribution Share Alike license, so you can take a copy of it, modify it, redistribute it, just as long as you give me credit. We're all good. All right. So this is kind of going to be a roadmap of what we're going to be looking at. First off, I'm not going to be talking about password managers, things like KeePass or LastPass or 1Password or any of those guys. This isn't something about how you can secure your passwords on your laptop or your phone. This is more from a developer perspective, where you're designing authentication applications for your customers, and they need to provide a username and password. What are you doing with that password on the back end? How are you going to store it? That's what this discussion is going to be about. So I'm going to talk about the different password hashing algorithms that are available to us right now. I'll look at a brief history of how we store passwords to disk. As with any security discussion, you always need to talk about your threat model and your adversary. So I'll cleanly and very clearly outline what that is. We'll look at some different ways to store our passwords. Then we'll try and revise our threat model and adversary. And then we'll finally conclude with some more modern alternatives. So let's get started. First, a brief history of storing passwords. The first known instance of actually making an attempt to store passwords securely was with the Multics operating system. Multics was a time-sharing operating system by MIT and GE and a couple of researchers at Bell Labs. It was a precursor to Unix. And the way they decided to store the password was by encoding it as a number and then taking the square of that number and storing the squared result. Obviously, this isn't great because I can just take the square root of the result and get back to the original password. So it was not long before they decided to add a private key, basically. They called it a mask, but a private key, and they would take the square of your result, and it with that mask, and then store the result. So unless you knew the mask, you would struggle reversing what was stored on disk. Unix stored their passwords historically in etcpasswd. Many of you are probably familiar with this file. That didn't last long. It eventually got moved into /etc shadow. etcpasswd is world writable by all the user accounts on the system. This is necessary for all sorts of applications who need to do any sort of user accounting, any sort of authentication. But that also meant that the password was world readable. So we needed to move that to something that was not. And so the password got moved to etc shadow, which is only readable by root. And we could keep the account names in the etcpasswd. Unix decided to create their own password hashing algorithm that they called crypt. And I put that parentheses 3 there. It should be installed as a man page on your computer. You could just say man space 3 crypt, and that could pull up the documentation on that password hashing algorithm. It was based on DES, which we now consider broken. The EFFs successfully demonstrated that. But Unix used crypt for a long, long time. It wasn't until, I don't know, the mid-90s that started changing. Because of the problems with DES, we started looking for alternatives. And one-way hashing functions look promising because they're one way. If I provide the password and get a hash out, you can't reverse that hash to get back to what I provided. It's a lossy compression function, basically. So you would have to brute force a number of tries and see if your results compared to the match, if they matched what was stored on disk. The problem with something like this, though, is by doing that brute force, I can build a database of passwords to hashes, right? And these are known as rainbow tables. And they were an effective way of reversing hashes back to their original input. There used to be a distributed computing project at freerainbowtables.com. You installed the Boink client, and you could help contribute to, I believe it was approaching 10 terabytes of rainbow tables. Salts were the way to thwart rainbow tables. By adding a salt is nothing more than just a random string of data. If every time you change your password, that string gets updated, then rainbow tables are no longer effective, because now that salt needs to be computed in addition to the provided password. And if the salt, let's say, is made from 8 characters of base 64 characters, and I have 64 to the 8 possible salts that random string could be. So my rainbow table just grew to 64 to the 8 times larger than initial. So salts are a way to thwart those rainbow tables. Windows has had a rough time with storing passwords securely on disk. Windows NT introduced LANman and NT LANman password storage. Neither one of them were salted, which made rainbow tables effective. And I believe the freerainbowtables.com website is still up. A good large chunk of those 10 terabytes are LANman and NT LANman pre-computed hashes. The problem with LANman and NT LANman was they decided to convert your password to uppercase, then pad it to a 14 bytes, and then split it into 7 byte chunks. The problem with this is 2 to the 7, let's just do a little bit of math here, is half the size of 2 to the 8. And it's a fourth the size of 2 to the 9. And it's an eighth the size of 2 to the 10, right? We grow exponentially. So 2 to the 14 is 2 to the 7 times bigger than 2 to the 7. It's considerably larger. So by splitting it into smaller chunks, we've greatly weakened the security of the password hashing algorithm. Because 2 7-byte passwords are easier to find than 1 14-byte password. So unfortunately, NT LANman and LANman have had historic problems with Windows, and it's a fast password hashing algorithm, which we'll see in a sec, turns out to be problematic. So let's talk about our attackers, our adversary, and our threat model. Our threat model is that, first off, our password database gets leaked, okay? For some reason, maybe the human resource department manager opens up a zip out of an email that compromises her computer. That goes through the network and compromises additional machines. Long story short, our password database for our customers has been compromised. So what we need to understand about our attackers is if we make the assumption that they have infinite money, infinite computing resources, and infinite time, then we'll be able to properly identify how we need to secure passwords. But if we make the assumption that they're going to be hacking this on laptops or on, one-use servers, then we're grossly underestimating the threat that our attackers possess. So we need to assume that the attackers are always more powerful than our defenders. And that threat model includes not only CPUs, but it includes highly threadable GPUs, and even things like FPGAs, field programmable unit arrays, and ASICs, right? These can be built on the cheap. They're substantially more powerful than GPUs or CPUs because they're dedicated hardware for a specific task, and they don't do anything else other than that task. So our defense then has been, unfortunately, to enforce password complexity, which turns out to be ambiguous. Different organizations will have different requirements on what they define as a complex password. this is outside of the scope of the talk. If you want to see me afterwards, I can give you a rigorous mathematical proof on what makes a secure password and what doesn't. But unfortunately, organizations, math is hard. It's not hard for me. I got a degree in mathematics, so I like math. But for most people, especially like the C-suite types and the management types, they don't like math. And so they'll make requirements such as a rotation policy. Got to rotate your password once every 90 days or once a year. They'll do these other things that make them feel secure when in reality, we're just putting Band-Aids on the problem. So here are some things that we need to avoid as developers when we're designing our password database. Obviously, let's not store it in plain text or do some sort of fancy encoding mechanism like base 64 encoding the plain text or hexadecimal encoding the plain text. This isn't buying anyone anything. And if you had a disgruntled employee at your organization who decided to take you down with it, he's got the keys to the kingdom. This isn't something that we want to deal with. So just avoid the plain text, avoid the plain text encodings. Avoid vanilla MD5 or SHA-1, SHA-2, or even the newly baked SHA-3. I'm going to explain why. I'll show you some good reasons why, but the problem is they're just fast. And it turns out that we don't want fast. We want reasonably fast for our customers. I mean, I don't want them to wait for a minute for the authentication to succeed. But at the same time, I don't want my password cracker to be going at 300 million password guesses per second either. So if I can limit him but still be responsive for the customer, I'm in a good spot. MD5 and SHA-1, SHA-2, SHA-3 don't provide this. We should avoid crypt, the Unix crypt. We should also avoid MD5 crypt, which was the replacement for the Unix crypt. Still common in some older Linux distros. In fact, we should avoid any general purpose one-way hashing function. We should absolutely avoid encryption, and we should definitely avoid our own design. You've probably heard the phrase, don't roll your own crypto. This applies here. Don't get creative with what you think is secure, what you think is super hard to figure out. We've already got best practices. I'm going to go over these best practices. Just follow the best practices. Don't try and get creative with your own design. So why shouldn't I use generic password hashing functions, things like SHA-1 or MD5? The problem turns out to be speed. While we certainly, like I mentioned, want things to perform for the customer, we don't want them to sit and wait forever for the authentication to succeed. At the same time, we don't want to give all this speed to the password cracker also. Right? We want to intentionally slow them down. So we need to find that sweet balance, or that sweet spot, that balance. And it turns out we can do this through what we call cost factors or work factors. We're going to introduce a work factor where isn't noticeable for the customer, but when you start to add up these iterations, is very noticeable for our adversary. So I want to introduce Jeremy Gosney. Who here knows by name Jeremy Gosney? Who's familiar? That's a sad crowd. That's okay. I didn't know him a year ago either, to be fair. Jeremy Gosney is a professional password cracker. He owns a company called Sagitta. You can go to sagitta.pw, and he will sell you password cracking machines. He has racks, data centers that are dedicated strictly for password cracking. He recently acquired, and he calls this a hobbyist password cracking machine, the 8 NVIDIA GTX 1080 GPUs. Okay? Put them in a box, got Hashcat 3.0, and then started benchmarking all of the password hashing algorithms that Hashcat supports. And this is what we see with these generic password hashing functions. In this 8 GPU cluster, MD5 could do 200 gigahashes per second. That's 200 billion MD5 hashes per second. Right? SHA-1, 68 billion per second. SHA-256, 23 billion, 9 billion, 6 billion. Okay, we're moving. My laptop, I don't think gets into the double millions at best when I'm doing these. But here we're in the billions of guesses per second. And this is just one password cluster, right? Hashing cluster. I think this cluster costs with those, what, how much do those GTX 1080s cost? Like maybe $1,000 a piece. So $8,000 for the GPUs, put in another $2,000 for the hardware and the necessary stuff. You're in $10,000 for a box. That's feasible for a hobbyist. Get 5 or 6 of those, that's feasible for a small corporation. This isn't a significant cost if this is the data that they're interested in. So why shouldn't we use MD5 crypt then? MD5 crypt was designed as a replacement for the DES crypt from Unix. The problem with MD5 crypt is it does introduce a cost, but that cost is hard-coded at 1,000 rounds, which means you input your password, it goes through the algorithm 1,000 times, and then spits out the result. So with that 8 GPU password cracking machine, we can see with MD5 crypt, I'm limited down to 80 mega hashes per second. That's a far cry from the 200 gigahashes I saw with raw MD5. So the cost factor is helping, but the question is it helping enough? And can I do better? Turns out this isn't good enough. 80 mega hashes per second is still far too fast that we want to give our adversary. We can still get much, much better while still also providing a responsive authentication time for our customer. So here's what I'd recommend in best practice. Who went to Open West earlier this year? A few of you? Did any of you guys, I gave the same presentation there. Did you guys attend this as well? Yay, nay? Okay. In May, I did not recommend Argon 2 as a production quality password hashing algorithm. I've changed my tune. Argon, and I'll talk about Argon 2 in more depth, but Argon 2 is a recent password hashing algorithm that just won the password hashing contest. They were looking for the best algorithm that provided the most security with a number of other factors, and this came out on top. Usually in cryptography, we're not excited about brand new algorithms. I mean, we are, but we want to let them bake for a while, let cryptographers attack them, let mathematicians attack them and try and weaken them. And if they kind of withstand the test of time, then we start to get more comfortable with using them, right? Then we can start recommending them for production. The case of the password hashing contest, it was a contest that lasted 3 years, and Argon 2 was already, the specification was already designed a year before that, and it's based on algorithms that have already been thoroughly vetted. So I've decided to change my tune from May to now. I would go ahead and recommend Argon 2. I also chatted with the inventor of Argon 2 on Twitter and got some warm fuzzies about its security margins. So, but we'll look at some others. So Argon 2 I'd recommend, then followed by scrypt, and then bcrypt, which probably most of you have heard of. Scrypt and bcrypt are really popular. We'll look at SHA-512 crypt, SHA-256 crypt, and PBKDF2, the password key derivation function. All of these guys have that cost factor that we're looking for. And all of these cost factors are tunable. So I can change that cost factor based on what I'm looking for from my application. So let's start with the SHA-256 crypt and SHA-512 crypt. What is it? It was designed after MD5 crypt by Ulrich Drepper, who was the main developer of the GNU libc library. He modeled it after MD5 crypt, but rather than hard coding a work factor, he decided to make that work factor tunable. This is the default password hashing algorithm for Linux. If you've got Red Hat or Ubuntu or Debian or SUSE or Slackware or really any of the Linux distros, you're very likely using SHA-512 crypt as your default password hashing algorithm for the local accounts. It does default to a cost factor of 5,000 iterations, but like I said, that's tunable. On my laptop, I've changed it to 520,000 just because I can. It takes about 5 seconds to authenticate, but it's my laptop. This isn't an interactive web page with thousands of customers is I can wait the 5 seconds for myself to log in. It's not a big deal for me. Then if my SSD gets compromised, at least I have some peace of mind knowing that 8 GPU password cracking machine is going to be sweating trying to recover my password. And maybe that's not even a threat model I should be concerned about with my laptop. But regardless, it was tunable. I made the change. Also, SHA-256 crypt and SHA-512 crypt provide an automatic salt. Remember how we talked about those rainbow tables, these pre-computed hash tables? We like the salts because they introduce a random component. And the larger the space of that random component, the larger that pre-computed table needs to be. So SHA-256 crypt and SHA-512 crypt automatically provide salts by default. Every time you update your password, the salt is reset to a new value, and every user will have their own random salt. So if we look at the benchmarks then at that 8 GPU password cracking machine, SHA-256 crypt at the default of 5,000 iterations could only work at 3 mega hashes per second, and the SHA-512 crypt at 1 mega hashes per second. It's interesting why the big, I mean, that's a 3 times difference between the two. Why the big gap? SHA-512 is designed for 64-bit processors, where SHA-256 is actually designed for 32-bit processors. I don't know, I'm guessing, but I don't know what hardware Jeremy Gosney had when he was running these benchmarks, but I'm guessing it was 32-bit hardware, which is why the SHA-256 crypt is 3 times outperforming the SHA-512 crypt. Okay, let's move on. Bcrypt. Who here has heard of bcrypt? Yes, common. First thing to set straight, bcrypt is not Blowfish, and Blowfish is not bcrypt. They are 2 completely different things. Bcrypt is designed, however, after the expensive key setup in Blowfish. And I think that's where the confusion comes from. Blowfish was designed by Bruce Schneier, who's a very popular cryptographer, security expert. But bcrypt took that function, that expensive key setup, out of Blowfish as the model to base the password hashing function on. But Blowfish is an encryption algorithm. Bcrypt is a password hashing algorithm. Very different. One can reverse a string of text, the other can't. Okay? So they are different, just for that clarification. Just like with the SHA-256 crypt and SHA-512 crypt, it'll automatically generate a salt. You could provide one if you would like. Otherwise, it'll automatically generate one. So you don't have to worry about salt maintenance with bcrypt. It has a customizable exponential work factor. With SHA-512 crypt and SHA-256 crypt, it was linear, right? I could do 5,000 iterations or 5,001, right? Which is just 1 extra iteration. 10,000 would be twice as many as 5,000, obviously. In the work factor with bcrypt, though, it's exponential. If I give it, say, the recommended work factor is 10, that means 2 to the 10 iterations. If I were to give it a work factor of 11, then that would be 2 to the 11 iterations, which is twice as many. So a work factor of 11 is twice as difficult as a work factor of 10. Okay? So we have that exponential curve. Bcrypt is available for the Linux OSs. There's a package called libpam Unix 2. Ulrich Drepper decided against bcrypt because bcrypt isn't standardized in any government specification like FIPS or by NIST, right? So that's why he developed SHA-256 and SHA-512 crypt, because SHA-256 and SHA-512 do have the NIST blessing. They do have that FIPS blessing. And Red Hat tries to be a FIPS compliant operating system. It's important. And so that's why he decided not to implement bcrypt, which had already existed when he designed those 2 algorithms. So there's, if you look online, do a little bit of searching with Ulrich Drepper and bcrypt, you'll see some of the hate mail that he's received and some of his heated responses as a result. But there is a separate pluggable authentication module, separate PAM module, where you can install it and get bcrypt if you want that for your Linux OS. And I should say also that bcrypt is vastly supported in all the programming languages: Ruby, Perl, PHP, Python, C, Go. Name one, there's a library available for it, likely on GitHub. So if we look at the bcrypt benchmarks, interestingly enough, or I guess not Jeremy Gosling, but Hashcat itself defaults to a work factor of 5 when you're doing the bcrypt benchmark. Because the recommendation is 10, even though I didn't have access to this cluster, I just assumed that a cost of 6 will take twice as long as a cost of 5 and so forth. So I worked the math out, and this is what you could expect with a cost of 10. So at a cost of 5, you're looking at 105 kilohashes per second. With a cost of 10, you're looking at 3 kilohashes per second. Just to remind you, we're now in the thousands, right? 3,000 hashes per second versus the 200 billion that a vanilla MD5 gave me. So we're considerably more expensive for my adversary. Let's look at PBKDF2. PBKDF2 stands for a password-based key derivation function. There was a version 1, there is a version 1, but it turned out to have some weaknesses, and so version 2 is the next logical step. It was developed by RSA Laboratories, and it's standardized in their PKCS documents as PKCS number 5. And it's also standardized in RFC 2898. PBKDF2 uses what you would call a belt and suspenders approach. I have a link to, I've blogged about this in depth on my blog. So if you want to get a lot deeper into it, the link will be coming up here in a few seconds, a few slides. But I discussed the password, or the belt and suspenders approach to PBKDF2. Basically, PBKDF2 breaks it out into parallel individual units, and those all work to a result that gets brought together at the end, right? So if I have 7 or 10 separate pieces, there's going to be 10 single outputs, and all these are exclusive or somehow mathematically related, those outputs, and I get my results. So kind of the belt and the suspenders approach. What's interesting with PBKDF2 is it's actually designed for key derivation. It's a password-based key derivation function. So this is what we use when we need an AES key or an RSA. Well, there's a separate key derivation function for RSA stuff, but we're using this to build encryption keys. Turns out that this is actually a good way to, a good thing to use for password hashing as well. PBKDF2 gives us an arbitrary output. I can say I need 128 bytes of key material, or 200 bytes of key material, or 512 bytes of key, whatever, and it'll work until that key material size has been met. So for passwords, I could just say, give me 256 bits of material, key material, and that's what I'll use for my hash that I'm going to store. It has a cost factor. It's linear, a linear cost factor. The default, or I shouldn't say it doesn't have a default, it's completely programmable, but the recommended iterations in 2000 was 1,000 iterations. Well, that's not really sufficient given today's password cracking machines. OS 10 right now actually randomizes that cost factor. If you have an OS 10 machine, OS 10 uses PBKDF2 for their password hash, and they default anywhere between 30 to 50,000 iterations. Again, that number is randomized. PBKDF2 will not automatically generate a salt. So as a programmer, you're going to have to manually provide that. And I'm going to say that if you're going to do that, your salt should come off of the dev urandom device. Okay? Don't get creative with some fancy way to create a salt. Just grab random data off of the random number generator and use that for your salt. Salts are not designed to be secret. In fact, most password databases, the salts will be right there with the hash, and that's perfectly okay. The only purpose of a salt is to thwart the pre-computed tables. So if the database gets leaked, sure, the adversary's got the hash and the salt. So now he can use that salt with the password to start working on the hashes. He doesn't have to go through, however many salt guesses before he moves to the next password. But we're not relying on the security of the salt to prevent him from discovering the password. We're relying on the security of the password hashing function, specifically the work factor that'll prevent him from getting to my password. So having the salt public is not a big deal. It's not meant to be secret. So randomize it, store it with the hash. In fact, this is what bcrypt does. The first 32 bytes, I think, these 24 bytes of the hash itself is the salt. So looking at some PBKDF2 benchmarks, again, Hashcat defaults to 1,000 rounds. This was the recommendation in 2000. And so this is what we see with PBKDF2. PBKDF2 relies on plugging in a hashing function. Okay? In and of itself, it doesn't do anything. I need to provide some sort of hash to get PBKDF2 working. So in this case, I'm using HMAC MD5, HMAC SHA-1, HMAC SHA-256, and HMAC SHA-512. HMAC just stands for a hash-based message authentication code. This is what is used to authenticate data across endpoints. I can get into the details, but those are the separate things that were used in the benchmark, and we can see those results everywhere from 59 megahashes per second down to 3 megahashes per second. All right, that table's kind of small. I don't know if you can see that very well. Let me make it bigger. So this is a comparison table of bcrypt, SHA-512 crypt, SHA-256 crypt, and PBKDF2. What I'm looking for here is when you're building your application and you're going to do your authentication or your key derivation, suppose you are designing a password manager, right? Maybe in .NET or Windows users, I don't know. And you want that they're going to provide a master passphrase that will decrypt the password database. You want to use an expensive password hashing function when they provided that passphrase, right? So in the case of an interactive login, I've highlighted in green, and in the case of a key setup like a password manager where it's okay that they wait a couple seconds, I've highlighted that in red. So I've decided to target about half a second for interactive logins and about 5 seconds for non-interactive, right? Or offline things like a password manager. This is something you should be thinking about when you are designing the app. How long are you willing to wait, or how long are you willing to have the customer wait for the authentication piece? Is half a second too long? And can your hardware support it? If you've got 1,000 people authenticating frequently, can your hardware support the load of each of those waiting half a second as part of that authentication mechanism? Maybe you need to tune that down. Maybe you have enough hardware you can tune it up. Regardless, I targeted half a second for interactive and 5 seconds for localized, like password managers, for like encryption keys. So for bcrypt at half a second, and these, by the way, these are timings on my laptop. This is a Lenovo T61. This is when Intel first introduced the Core 2 Duo. I purchased this laptop in August of 2007, and it's still running like a champ. But, so yeah, maybe a cost of 13 for bcrypt on my laptop might be a cost of 14 on your hardware, or maybe even 15. You'll need to just benchmark that and see. But in case of my laptop, cost of 13 for bcrypt gave me a half a second on the interactive login, 640,000 iterations for SHA-256 crypt and SHA-512 crypt, and 640,000 iterations for PBKDF2. And if I wanted to target a 5-second key setup, then we were looking at a cost of 16 on bcrypt, just over 5 million on the SHA crypts, and just over 5 million on PBKDF2. Okay. All right, moving forward, scrypt. Scrypt was developed by Colin Percival for his Tarsnap backup service. In fact, this has come up a couple times at the conference already. People have asked what to use for a secure backup for a third party. Obviously, the most secure backup is one that you control and no one else controls, right? That's yours on your local infrastructure. But if you need to do offsite, if you have some other needs and you need to rely on a third-party vendor, I would recommend personally Tarsnap. I don't work for them. It's not a sales pitch, but it is a secure backup service. And scrypt was designed as part of encrypting the backup locally before it gets sent to the Tarsnap servers. scrypt is designed to not only be CPU expensive, but also RAM expensive. The costs we've looked at so far have all just been CPU costs. bcrypt, PBKDF2, the SHA crypts, they're only CPU costs. How much time can I put on the CPU? scrypt introduces a memory cost, right? The idea is that GPUs or FPGAs or ASICs are going to be limited on memory. So if I can afford 16 megabytes or 32 megabytes or whatever of RAM to dedicate as part of the cost in producing the hash, then maybe I can thwart these targeted attacks. So I can customize not only the CPU work factor, but the RAM work factor. And Colin recommends that the result is a 16 megabytes of RAM. Unfortunately, I can't fine-tune the CPU cost versus the RAM cost. Instead, I get this CPU cost, which is the capital N, and then I have this R and this P. And these are just, the P is a product factor. The R is, I want to say it's a register. I'd have to look. I don't remember the exact acronym for it. But there's a math equation where I multiply these and add these together, and that'll tell me how much RAM gets used as a result, right? So I don't have like a RAM knob I can tweak. I just have these three guys, and then I need to do the math to see what the RAM cost ends up to be. But he recommends at least 16 megabytes of RAM. With Hashcat, unfortunately, it targets 128 kilobytes of RAM. So in that case, it produced 3 mega hashes per second. Again, that's not the recommendation. So I needed to do the math and move it up to the recommendation of 16 megabytes of RAM. And according to my math, even though I didn't have access to this hardware, it should produce around 24 kilohashes per second. Okay. All right, here we go. And here is my scrypt table. Again, we are targeting green, a half second for interactive logins, and red, around 5 seconds for non-interactive logins. So because you can tweak the N, R, and P, this kind of gives you a lot of knobs now, and you kind of get all over the place. So I wanted to target that 16 megs or higher. And so I have that RAM column. When it's 16 megs or higher, it's green. At 8 megs, I made it black because it's not the recommendation. But there's an interesting mathematical proof that can be done that if you do less than 8 megs of RAM, scrypt actually ends up being weaker than bcrypt. So that's why that number went red. So recommendation is 16 or greater, but definitely make sure you're above 8. Otherwise, you're doing yourself a disservice. So here are some of those results. N equals 18, R equals 8, P equals 1. Or I could bring, if I brought the P up to 2, then my N can go down to 17. If I bring the P up to 4, my N can go down to 16 on the interactive, and analogously for the non-interactive. Get back to, all right. So that's scrypt. Now let's talk about Argon 2. Argon 2 is the winner of the password hashing contest in 2015. This is a contest that went on for 3 years, and there were cryptographers all around the world. It was an open contest, so cryptographers could submit their design, and then there was a panel that would go through the submissions and then go through the papers that cryptographers would submit on the analysis of these designs, and then weed them out, ultimately coming up through a final winner. If you're familiar with AES, AES had a similar competition back in 2001. NIST opened up to the world and said, we need a replacement for DES, and we want to have all the cryptographers across the world submit us their algorithms, and then we'll have those same cryptographers and anybody else submit papers on analyzing these algorithms, and we'll go through a number of different rounds, round 1, round 2, round 3, weeding out the weak ones and hopefully narrowing in on the strong ones, and then we'll pick a winner. Same thing with the password hashing contest, and Argon 2 came out on top. It exists in 2 versions, Argon 2D and Argon 2I. They both have different goals. Argon 2D is designed to thwart GPU, FPGA, and ASIC cracking resistance. Argon 2I, on the other hand, is designed to be resistant against side channel attacks, such as timing attacks. So when it comes to passwords, you'll probably want to stick with Argon 2D. But when it comes to key derivation, Argon 2I might be more important because of that side channel resistance. Argon 2D does have a CPU knob, a RAM knob, and then a parallel knob. How many CPUs or how many parallel processes you can dedicate to the working of the hash. What's interesting is, because now I have these separate knobs, I don't want to tweak the CPU too much without tweaking enough RAM, right? Otherwise, I'm really no better off than bcrypt or any of the CPU-intensive algorithms. By the same token, I don't want to tweak the RAM knob too much without the CPU. Otherwise, people who have large caches, like on-die caches or maybe large SSDs that can be extendable virtual memory, I'm not getting outside of that either. So I need to tweak both. I need to be aware that I need to tweak my CPU cost, and I also need to tweak my RAM cost. Interestingly enough, there was some attacks on Argon 2I, but because this is side channel attacks, it's really not relevant for our password discussion if you're using Argon 2D. However, this was fixed in version 1.3 of the spec. Hashcat does not have Argon 2D, Argon 2 at all in any algorithms in the project. So I don't have any benchmarks to give you, unfortunately. At least not comparable with the 8 GPU cluster that we had. But this is what I was tweaking around with on my laptop. And I saw that for a CPU cost of 128 iterations, a memory cost of 12 using 4 processes, I was about that half a second for an interactive login. Or if I tweaked the CPU up to 4096, then I hit 5 seconds for like symmetric key derivation. And coming up on that table, make it a little bit bigger, we can see that there. By the way, this AE7.ST, I'm a ham radio operator, and my call sign is AE7ST. So I purchased the AE7.ST domain. And that's my own personal URL shortener. So while technically it is tracking you, I honestly really am not. I've got better things to do with my time than see who's been clicking my links. But this just goes to my own personal blog post, and the title is really lengthy, so this just fit better on the slide. But if you go there, this will point you to a blog post that'll do some discussions about Argon 2, scrypt, bcrypt, and so forth. All right, bcrypt has a weakness that I failed to mention when we were talking about bcrypt. Bcrypt has a C null repointing problem. For those of you who are C programmers, you're probably aware of the null character. When bcrypt encounters the null character, it resets the pointer back to the beginning. Now for a password, you're probably not entering the null character. You're probably entering some ASCII text. The problem, though, is bcrypt has a limit of 72 total bytes that it'll hash. So if your password, my Google password for the longest time used to be 84 characters in length. Bcrypt can't handle that. So a workaround is to what we call pre-hash. I could pre-hash my password, maybe with SHA-512, and then go ahead and apply bcrypt to that result. Then I could have a 128 character password, 200 character, 500 character, apply that to SHA-512, and that will fit within the 72 bytes because it's only 64 bytes in length. And then I can bcrypt it. The problem is, though, that your SHA-512 or any other hashing library is probably producing raw binary, raw bytes. It's not ASCII encoded. And that's where this C null character becomes a problem, because the null character could be part of that output. And then we encounter this bug where the pointer gets repointed and bcrypt. We're not getting the security out of bcrypt that we want. So if you are going to pre-hash your password before bcrypt, this is what I would recommend. So go ahead and apply the SHA-512 to the password, then base 64 encode it, or hexadecimal encode it. ASCII encode the binary. So we have plain regular ASCII text characters. Then you can go ahead and apply the bcrypt and you'll be okay. Now, I know I gave you caution about not coming up with your own design, and that's good advice. This isn't my own design. This is actually considered a best practice case by the security community at large, that if you're going to pre-hash, this is the direction that you need to go. All right, scrypt also has some weaknesses you should be aware of. If you choose weak parameters like we talked about, it can actually get weaker than bcrypt. This link here will take you to a blog post by a guy named Anthony. He goes by IRC Maxell in IRC. He's a smart mathematician. He clearly goes through a rigorous proof that shows if scrypt is using 8 megs or less, you actually end up weaker, or pardon me, less than 8 megs, you end up weaker than bcrypt. So you need to target at least 8 megs and go north of that. Colin Percival, the author of scrypt, recommends 16 megabytes of RAM. So if you just stick with the recommendation, you'll be okay. And then finally, Argon 2. Argon 2, I did have a weakness where a single pass was actually using 1/4 to 1/5 the desired RAM that you were looking for. And this was fixed in 1.3 of the specification. However, this was only valid for 1 or 2 iterations. You're probably doing 128 or 500 or more, so it wouldn't have been applicable anyway. But regardless, it did get fixed. And this was only applicable to Argon 2i. This was not applicable to Argon 2d, which you should be using for your passwords. So here's a summary of the best practices. I think you should target roughly about a half a second for interactive logins, like web pages, or 5 seconds for symmetric key derivation, like a password manager I'd be running on my laptop. If that were the case, then these are the separate costs for bcrypt, SHA-2crypt, PBKDF2, scrypt. Notice scrypt, actually, I can have a few couple parameters. I can either put it CPU intensive with the R equals 1, P equals 1, or back off on the CPU and increase R equals 8 and P equals 1. Regardless, both target at 16 megs. And then with Argon 2, you just need to balance it. It can be all over the place, but make sure you're targeting both enough CPU and enough memory. Okay, right on time. Are there any comments, questions, or rude remarks? So the question is it worth installing non-standard stuff? What do you mean by non-standard stuff? Yeah, Argon 2 is a new... Okay, so you're talking about programming languages. Okay, Argon 2 is seeing a lot of support in programming libraries, but you will find ubiquitous, widespread support in all the languages with scrypt and bcrypt. So if you're not comfortable with Argon 2 yet, or maybe a library doesn't exist, then use scrypt would be my next recommendation. How do you pick one over the other? Guess what you're familiar with. Yeah. Question there. Which one? Question was, which one of these is going to irritate the NSA the most? Yes. Like I said, in order of preference, I would prefer Argon 2, followed by scrypt, and then bcrypt, and then after that. But really, so long as I think it's less important that you're irritating the NSA and more that you're not irritating your customer base. So I think there's a balance there. But as long as you have that appropriate time limit for your customer, but you have the appropriate cost with these best practices, I think you'll be a good thorn in the NSA side. So, any other questions? All right, thanks, guys.